Hey everyone, welcome to The Explainer. So today, we're diving into something that, let's be honest, might sound just a little bit dry at first, data analysis and statistics. But I want you to completely reframe how you think about this. Forget the textbook math for a second. Think of it more like a detective's journey. You, whether you're a researcher, a marketer, or a business owner, you are the detective. The raw data? That's your evidence. And we're going to use that evidence to solve some of the most complex, high-stakes, real-world mysteries out there.
Here's our quick roadmap for today's explainer. We'll start with the power of data. Move into descriptive versus inferential statistics, forming your hypothesis, parametric and non-parametric testing, testing the hypothesis, and finally, the final decision. Let's get right into it.
Section 1. The power of data. I really want to emphasize upfront that data analysis isn't just academic number crunching. In today's landscape, it's basically the ultimate tool for business survival. I mean, analyzing data is absolutely crucial because it stops you from just throwing money away on bad ads, right? It lets you track exactly how your campaigns are performing so you know your target audience's spending habits inside and out. Plus, it helps you spot exactly which parts of your operations are failing, so you can either scale back or cut those costs entirely. Ultimately, it's about making smart, informed choices to avoid incredibly costly pitfalls. But how does this whole process actually work? Well, it breaks down into 6 pretty straightforward chronological steps. First up, you gather requirements. You have to ask yourself, why are we even doing this? Second, you actually collect the data, maybe from surveys or direct observations. Third, you've got to clean it up, scrub out all the duplicates and weird errors. Fourth is the actual analysis part, using your software tools. Fifth, you interpret those results to form a real plan of action. And finally, step 6 is data visualization. This is the fun part, where you transform all that raw, messy information into charts and graphs that normal people can actually read and understand. Moving on to Section 2, descriptive versus inferential statistics. Let's build out our forensic toolkit. We really need to draw a hard line between the 2 main subcategories of statistical analysis. First, we have descriptive statistics. These do exactly what the name implies. They just describe a specific group. They look at summarized numerical data to show you exactly what happened in that one specific data set. Inferential statistics, on the other hand, that's basically a superpower. They allow you to take a tiny sample of data and use it to draw conclusions and generalize predictions about a massive, overarching universe of data. When you're dealing with descriptive stats, it really boils down to 2 main areas. First, you're trying to find the center of the data. That's going to be your mean, median, and mode. And second, you're figuring out just how spread out that data is. That's your measure of variability, which gives you things like the range or the standard deviation. It's really all about summarizing what is directly in front of you. But then, when we flip over to inferential statistics, we get a totally different picture. Inferential stats take this tiny little slice, the sample, and use it to make incredibly accurate predictions about the entire pie, which is the population. Think about it. You don't need to ask every single person in a country a question to figure out what the country thinks, right? You just need the right sample. Okay, Section 3, forming your hypothesis. If we're detectives, we obviously need a suspect. And in data analysis, our prime suspect is the hypothesis. This is essentially our tentative solution to whatever problem we're investigating. I absolutely love this quote from John W. Best, where he calls a hypothesis a shrewd guess. Actually, in research, a hypothesis is often referred to as a leap into the dark. It's this brilliant, educated guess about how things work based purely on the facts you've observed, which then acts as a compass to guide the rest of your whole investigation. Here's the catch, though. To stay totally unbiased while we test the evidence, we actually start with what's called a null hypothesis, the H0. This is our default position. It's essentially the zero difference assumption. It literally states that there is no relationship or no difference between the variables we're testing. We assume nothing at all is happening until the hard evidence absolutely proves otherwise.
Section 4, parametric and non-parametric tests.
All right, interrogation time. We have our suspect, the hypothesis, and now we need to decide which statistical test is best suited to interrogate it. You can think of parametric tests as your strict, by-the-book interrogator. They assume your data follows a normal distribution, that you don't have any extreme outliers, and that the variance is equal. They have strict rules for sure, but they yield incredibly trustworthy, powerful results. Non-parametric tests, however, are your flexible interrogator. They are distribution-free. So if your data is messy or skewed, or maybe you just have a really small sample size that doesn't fit the strict rules, non-parametric tests can step in and save the day. It's basically a decision tree for finding the truth.
Once you set up your null or alternate hypothesis, you move right into testing. And based on your data's specific rules, you either go left to the parametric tests, like a t-test or ANOVA, or you veer right to the non-parametric tests, like the chi-square. It's a very structured, logical workflow.
Which brings us to Section 5, testing the hypothesis. We are finally taking our suspect to trial to determine, once and for all, if our educated guess is backed up by facts. But during this trial, there are actually two ways we can totally screw up. If the null hypothesis is actually true, but we reject it anyway, we've made what's called a type 1 error. Think of this as convicting an innocent person. On the flip side, if the null hypothesis is false, but we accepted, we've made a type 2 error. That's basically letting a guilty person walk free. Our ultimate goal with all this statistical testing is to minimize the chances of making either of these errors.
Let's bring this into the real world for a second. Imagine a professor wants to know if her entire statistics class has a good grasp of basic math. She doesn't want to test everybody, so she pulls a random sample of just 6 students. Her goal? She wants to prove that the class's average score is above 70. Now, her 6 sample students score 62, 92, 75, 68, 83, and 95. So the big question is, using this tiny little sample, can she be 90% confident that the entire class would score above 70?
Well, first, we take those 6 scores and average them out. We find the sample mean is 79.17. We also calculate our standard deviation, which comes out to 13.17. That 79.17, that acts as our baseline evidence. Now, it's looking pretty good for the professor, since the sample is clearly above 70, but is it statistically significant enough to represent the whole class?
And finally, Section 6, the final decision. Time for the verdict. It's time to bring our detective story to a close. To get the final piece of the puzzle here, we use a parametric test, specifically a one-sample t-test. We plug in our sample mean of 79.17, our target number of 70, and our standard deviation right into the formula. And the result? We get a computed t-value score of exactly 1.71.
Okay, so what does 1.71 actually mean? Well, this is where we apply the ultimate golden rule of the trial, the decision rule. We take our calculated value of 1.71 and we compare it against the standard, tabular critical value that you'd find in a statistical table. If our calculated value is greater than that tabular value, boom, we reject the default null hypothesis. That means the professor was right, the class is highly proficient. But if it's less, she has to accept that her evidence just wasn't strong enough to make that claim.
And honestly, that is the real beauty of data analysis. It takes the total unknown and turns it into something you can actually measure. By gathering clean evidence, formulating a shrewd guess, and running it through a rigorous statistical trial, you can predict the behavior of an entire population just from a handful of data points. So I'll leave you with this to think about. How might you use an educated guess and just a small sample of data to solve a massive problem in your own business today? The tools are literally right there waiting for you. Thanks for hanging out with me for this explainer, and keep questioning the data.